Dalton's law of partial pressure. You're gonna love this one with all that decent amount of math that we've been doing. Um, this one is an easy one. Here's what this is essentially saying. Dalton's law essentially is saying that the identity of the gas does not matter. All gases, every type of gas, contributes equally to the pressure in a system. So, the total pressure, essentially what it's saying, of a mixture of gases is equal to the individual pressures from each gas in the mixture. Now we call these individual pressures, we call these partial pressures. So the partial pressure of a gas is the individual pressure. So like what's the pressure of each individual gas? So easiest problem you're gonna get all classes right here. What is the pressure of a container that contains 0.75 atmospheres of hydrogen, 1.25 atmospheres of nitrogen, and 0.85 atmospheres of helium? Well, the total pressure is equal to each individual pressure. So 0.75 atmospheres plus 1.25 atmospheres plus 0.85 atmospheres. And of course, we are going to get a total pressure of, what would that be? 2.85 atmospheres. Okay, now this goes the other way as well. If you know the total pressure, which is more common, if you know the total pressure of a mixture of gases, and you know all but one of the individual partial pressures, you can solve for the partial pressure of the gas you don't know. So that's super handy as well. Mole fraction, we are going to need to be able to use Graham's law of effusion. So mole fraction is a way to really represent concentration. The mole fraction of a gaseous system is equal to the moles of one of the gases divided by the total moles of gases in the system. Um, and you can get the partial pressure of a gas by taking the mole fraction of that gas times the total pressure. So, if I know that the mole fraction of a gas is 0.3 and I know the total pressure is 2 atmospheres, then the partial pressure of that gas must be 0.6 atmospheres. So this mole fraction formula is going to come in handy soon. Let's solve this guy though first. So a balloon contains 2.65 grams of helium, 5.65 grams of nitrogen. We got a total pressure of 4.88 atmospheres. What is the partial pressure of the nitrogen? So essentially what we're looking for here is we want the partial pressure of the nitrogen. In order to get the partial pressure of the nitrogen, we need the mole fraction of the nitrogen. And then we're going to multiply that by the total pressure. Now we have the total pressure. That's just 4.88 atmospheres. So if we can get the mole fraction of the nitrogen, then we can multiply that by 4.88 and get the individual partial pressure of the nitrogen. Well, how are we going to do that? We're going to have to convert the 2.65 grams of helium to moles of helium. We're going to have to convert the 5.65 grams of nitrogen to moles of nitrogen. And then we can take the moles of nitrogen divided by the total moles to get the mole fraction. So why don't you take a second to get started on that? I'll start writing this guy down. All right, so let's get you caught up to where I'm at. Hopefully you're past me, maybe even. If we need to get the mole fraction of the nitrogen, we use a Greek letter chi to represent mole fraction. So the mole fraction of nitrogen is going to be equal to the moles of the nitrogen divided by the total moles. This system only contains nitrogen and helium, so that's going to be the moles of the helium plus the moles of the nitrogen. So I divided the mass of the helium by its molar mass to get the moles of the helium. That's what's going to go in there. And I divided the mass of nitrogen by the molar mass of nitrogen. That's what's going to go in there. So our mole fraction is going to be 0.202 moles, divided by 0.663 moles plus 0.202 moles. So 0.202 divided by the quantity 0.663 plus 0.202. And we get 0.234. Now, it is a unitless number. Moles divided by moles is no unit. The mole fraction has no unit. And now we can get the partial pressure of the nitrogen. Take that mole fraction, 0.234, multiply it by the total pressure, 4.88. And the pressure from the nitrogen gas molecules in that system is 1.14 atmospheres, which means the helium is accounting for 4.88 minus 1.14. The helium would be accounting for the remaining 3.74 atmospheres of pressure inside that system, of course, adding up to the total pressure of 4.88 atmospheres. So mole fraction, okay, a little different. It's kind of like a percent, but for moles, right? Now we don't multiply by 100, so it's not a percent in that terms, but you take the moles of the gas divided by the total moles of gases, and we can get there that way. All right. Next up, Graham's law of effusion. We need effusion versus diffusion. All right, you guys are probably super familiar with diffusion. Diffusion is when a gas kind of just mixes with another, or when even any fluid mixes with another. So there you have example in that picture at the top of the food coloring being dropped in there, and the purple food coloring, diffusing throughout. If we were in a classroom and I opened a bottle of sulfur, that rotten egg smell from the sulfur would diffuse throughout the room. The sulfur gas, because sulfur is very volatile, the sulfur gas would mix with the air and it would diffuse throughout. And slowly, row by row, students would start to smell that sulfur gas till it worked its way all the way to the back of the room. You are probably familiar with diffusion. You are probably not super duper familiar with effusion. Effusion is similar, but it is when a gas leaves through a tiny pin-sized hole into a vacuum. Okay. So a little different, right? It's still the movement of gaseous particles, but it is through a tiny pin-sized hole into a vacuum. So you got to have a vacuum on the other side, okay? There was a guy by the name of Graham who figured out how gases, how to predict how fast a gas will effuse, and then it can be extrapolated to diffusion. I'm not going to make you solve this guy, okay? But I want you to look at this formula. This is called the root mean square velocity formula. And this formula allows you to figure out the average speed of a gaseous particle. It looks a little intimidating. It's really not that bad. It is the average speed, or root mean square velocity, of a gas is equal to the square root of 3RT over mW. Now, because this is kinematics, like speed, the universal gas constant, which we just learned about tonight, 0.08206, has been converted into energy units of joules per mole. So instead of atmospheres times liters over moles times Kelvin, this is converted into joules per mole times Kelvin. Same number, just been converted. Okay, don't worry about how to do that conversion. So, that R goes in here. Temperature, of course, still has to be in Kelvin. And the only thing is, because a joule is actually a Newton meter, and because a Newton is actually a kilogram times meter per second squared, so a joule is actually a kilogram times meter squared per second squared. All that to be said, because joules has units of kilograms in it, the molecular weights have to go in kilograms. So if you ever have to use this formula, and I'm not going to put one of these on the test, get the third test, okay? But if you ever have to use one of these formulas, or you ever had to use this formula in your life, just remember that that molecular weight is going to have to be in kilograms. Here's what this formula is saying, and this is what I want you to get out of this. It's saying that the speed of a gaseous particle is equal to 1 over the molar mass of the gaseous particle. What this is essentially saying is heavier gases move slower than lighter gases. And I think this is kind of common sense, right? Okay, it's kind of common sense. Heavier things, okay, are going to be moving slower than the lighter things. Now, the real reason for this, if you ask a physicist, is because temperature is a measure of the average kinetic energy of the particles in a system. So, if I have a mixture of gases, if they are all at the same temperature, okay, then they all have the same average kinetic energy. Kinetic energy is half of the mass times velocity squared. Okay, so if they have different masses, then they have to have different velocities as well in order to be having the same kinetic energy and same temperature. So the moral of the story here is lighter gases move faster than heavier gases. Why is that important? Well, that's important for Graham's law. Now, this is a formula that you will have to use. Graham's law allows you to determine compare how fast the different components within a mixture of gases will effuse. And it works pretty well for diffusion as well, but it's really set up for effusion, right? So tiny pin-sized hole, vacuum on the other side. How quickly do the gaseous particles leave, okay? This is not a typo. Here's Graham's law of effusion. It says the rate that the first gas effuses divided by the rate that the second gas effuses is equal to the square root of the molecular weight of gas 2. So these two go together, divided by the molecular weight of gas 1. These two then go together. So, you got to really make sure that you're pairing it up correctly. So I always struggle to think of a real world application for this problem. So here's the closest real world application to an effusion problem that I could possibly come up with for you. We're going to make one up just off of the top of our heads. So in order for effusion to be happening, you got to have a vacuum on the other side of the gas that the gas is exiting into. And where's a better place to have a vacuum than outer space? So let's imagine that you get abducted by aliens. Okay, it's a very practical application of this problem here. So you get abducted by aliens. Don't worry, they're friendly aliens. They're super nice alien folk. So you're gonna get abducted by aliens, okay, and they take you up on their mothership, right? And you're having fun, right? It's it's a good time. And they got oxygen gas in here so you can breathe. But these aliens, they did not evolve to breathe in oxygen gas. They actually breathe argon gas. They need argon. So inside the spaceship, we got a mixture of oxygen and argon gas. The oxygen for you, the argon for your alien argon breathing friend. And your alien friend here is flying around. He's trying to show off his spaceship to you. And he's going a little too fast, and you're going through a meteor field, and boom! Unfortunately, he hits a tiny space rock, cracks the windshield, and now we got a tiny pin-sized hole that our gases are going to effuse out into the vacuum of space in. And you're both going to die. It's very sad. You and your alien friend Alf are both going to die. But my question is, who's going to die first, right? So who's going to die first, and who's going to have to watch their new best friend die before they themselves die? Okay, so how do we solve this? Well, we're going to use Graham's law of effusion. We've got a mixture of oxygen gas and argon gas in our little spaceship here. And they're going to effuse, and Graham's law of effusion says the rate that gas 1 effuses divided by the rate that gas 2 effuses is equal to the square root of the molecular weight of gas 2 divided by the molecular weight of gas 1. So these two go together and those two go together. So it all comes down to what gas are you going to call gas 1 and what gas are you going to call gas 2. Doesn't matter to me. We can call the oxygen gas 1 and we can call the argon gas 2. So the rate that the oxygen effuses divided by the rate that the argon effuses is equal to the square root of the molecular weight of argon. Argon is weighing in at 39.95 divided by the molecular weight of oxygen, which is 32.00. So here we go. The square root of 39.95 divided by 32. The oxygen will effuse slightly faster than the argon. It will effuse at 1.12 times the speed. If I put that into a fraction, you can't. It's an irrational number, so never mind. Okay, but moral of the story, the oxygen, because it is lighter, is going to effuse a little bit faster. Why is that? The oxygen, because it's lighter, is moving a little faster than the argon. So that lighter oxygen is going to find the tiny pin-sized hole faster than the argon, which is moving slower, so it doesn't find the hole as fast. In reality, they're moving at almost exactly the same speed because they have such similar molecular weights. But that oxygen will exit a little faster, and unfortunately for you, you'll die first. And unfortunately for Alf, he's got to watch you die before he or she dies. And that's going to be the last thing they witness. And they know it's their fault. It's just so sad. So that's the most practical application of a Graham's law of effusion problem that I could possibly come up for you with. If you ever saw The Martian, Matt Damon, love Matt Damon. Okay, if you ever seen The Martian, there's that, which I didn't think was that good. People were losing their mind over that when that came out. I was like, yeah, it's okay. But anyway, if you ever seen The Martian, there's that scene where he like punches a hole in his spacesuit and he's flying around like Iron Man. That would be effusion. There's like a readout on his helmet, and I remember, I don't know, it's been a couple years since I've seen that movie. But I remember thinking, I was like, I don't know if they're obeying Graham's law of effusion there. But anyway, somebody rewatch that. Think of Graham's law of effusion when you see that next time.